Okay, today we are going to have a look at the torsion in structure. Now, we will have a look at how torsion is developed in a circular shaft, how it is related to a shear stress, uh, bending stress, and how to draw a torsion diagrams and find the torsion at the support. Now, what is torsion? Torsion is the turning moment about the x-axis of the member. Bending moment is across the length of the member. So bending moment is across that way, that's the bending moment. And torsion is like you just kind of turn it. In torsion, the length does not change. Now, this gives you the idea about the torsion. There is no torsion here. But if I put a load on that green side, like a bit higher load, then obviously the shaft will twist, and this twisting effect is because of the torsion. It depends on the material structure. It depends on the E, the modulus of elasticity of the material. It depends on the I, which depends on the shape of the material. Now, when we look at the torsion, if I twist it, we will come back to that one in another slide as well. If I twist that one, this line, if I draw a line here and I try to twist it, this line after torsion will be twisted here up. And this angle is known as the angle of torsion, angle of twist. Then I got the shear strain. Shear strain has a formula. This thing is shear strain. It's E dash, which is that length of the arc, E dash over L, which is equal to R theta over L, where L is the length, theta is the angle of the twist, R is the radius of the shaft. Shear stress has another formula. Shear strain. Shear strain is shear stress over shear modulus. Now, if you want to find the strain, strain is the total length and the change in length, and that is in radian. This is the main formula we actually need. And I will explain what the T is. L is the length, theta is the angle, G is the modulus, R is the radius, and T tau is the shear stress. Yep. Okay. Moving to the next one. How does the torsion develop in a structure? Now, we have the force. When we apply the force on the structure, what actually happens is it acts, we know pressure equals to force over area, we know that one. Now the force acts on a certain area. Now if I want to find out this area, the one that's highlighted one, I need a perimeter of that one, which is that circle, and I need a thickness of that one. So perimeter is 2 pi r, and the thickness, I call it delta r. Because I took the part of this radius, the total radius is r, and I multiplied that with a tau, because the real formula is this one. Shear stress, force equal to stress, shear stress and shear area. The shear stress here is tau, so force equals to tau times the area covered. The area covered will be 2 pi r multiplied by the delta r, which is a change in radius. Now, if you see an uppercase T, this uppercase T is the torque. If you see like that kind of T, this T is the shear stress. So that is a shear stress, and this is the torque. Shear stress. Okay. Then we have, ignore this one, ignore that bit here. We have the formula T over J equals to G theta over L, which is also equal to tau over R. This is the main equation we will have a look. Now, where J is the second moment of inertia, yeah, J is the second moment of inertia. We will talk about that in detail. Yeah. Okay. Now, for the solid, if you got a solid bar, the value of the J is pi r4 over 2. For a hollow bar is pi over 2, same formula, r outer radius minus the inner radius, both to the power 4. We cannot write that one like this. We cannot write that one like this. It's give you a different answer. It has to be a 4 here and a 4 here. Yeah, like that. Inner radius, outer radius. Yeah. Okay. Now, when we try to apply a torsion, the shear diagrams looks like that. Yeah, this is how the shear diagram is going to look like. We will discuss that in detail. Again, just to give you some units and what's meant by each and every. Okay, the torsion, the torque is T. This is the torque. The torsion constant, you can call it torsion constant or inertial second moment of inertia. Yeah, inertia, J. Stress, this is the shear stress. This one is the shear stress. So that is a shear stress. Shear modulus is the G. The lengths, which are radius and the length, that's the unit we use. You can use the meters as well, but because the dimension is not going to be very long, we prefer millimeters. Yeah, but up to you which unit you want to use. If we are looking for the Young's modulus, is that one. This is for the bending. This is the bending one, and this one is for the torsion one. Now, let's say we got a question. Find the maximum torque exerted on the diameter is given. Maximum shear stress is given 75 Newton per millimeter. That should be a square. That's a millimeter square. Yeah. Which would be better, a hollow or a solid? We have an equation here. So we are given the equation. We will use this equation to find that one. So let's go on the next page. First, we need to find out the J for the bar, solid bar and a hollow bar. So we do one solid, one hollow. Now, if you have a look here, they gave you the outer diameter 40. Yeah, so I'm just going to put that value here. So the radius is going to be 20. So here pi r4 to the 2, that is the formula for the solid, for the J. This is the formula for the J for the solid. Okay. So I put that in calculator and I will have this value. Now I will do for the hollow one. For the hollow one, let's have a look at that one. 8 millimeter thick. If the hollow is 8 millimeter thick, which means the outer is from here to here is 20. So I need to reduce the 8 from here and 8 from here. So 8 plus 8 is 16. 40 minus 16. 40 minus 16 is 24. Okay. So this is 8 from here. The thickness is 8 and the total was 20. So if I want to find out that one, that's going to be 12, isn't it? Make sense? The inner one. So I put the inner one 12 because we're doing radius. 24 minus 12 to the power 4. That will give me the value. So you actually have a look. This is the J here is a lot bigger than the J here. Yeah. Okay. Once we got the J, I need to find out, the question is, find the torque for different bars. So I got the formula for the torque. Torque equals to J times torque equals to J times the shear over the radius. Now for the hollow, I need to do the calculation for the hollow and I need to do the calculation for the solid. So let's say for the solid, I got the value for the J 2.5 times 10 to the 5 multiplied by the torque was 75. Why it was 75? Here you go. It says 75 Newton over millimeter. Because everything is millimeter, I keep in millimeter. Divided by the radius. Radius was 20. I put the 20 there. That will give me 0.9 kilo Newton meter. Yeah. Okay. Why it got kilonewton meters? Because that's millimeter, they will kind of cancel. We have a look at the units in a minute. And that will give me 0.82. So I got the, both values. Now, which mean the solid bar, it's a solid bar, it's 0.9942. And then we got a hollow one, which is 0.82. In terms of efficiency, the hollow bar is more efficient. Okay, so hollow bar in this case is more efficient, even though the weight value is less, but with amount of the material utilized, it's more efficient. Okay, now let's have a look at the maximum stress exerted on the same bar by torque of 1 kilonewton meter. So if I got a torque of 1 kilonewton meter, if I got the solid one, because then I need to rearrange the formula. The formula, I need to make torque the subjects, T equals to TR over J. If you remember, the formula, the real formula is that one. So I need to make that thing a subject. So ignore that one because the other thing is not given. I can go, sorry, it's a funny one. That one equals to T times the R over J, where that is a shear and this T, the proper T is the torque, R is a radius, and J is a second moment of mass. So I put that one for the value, they gave us the value of 1 kilonewton meter. That's the torque, yeah? So torque is 1 kilonewton meter. I converted the kilonewton into Newton. So that is 10 to 3, yeah? Now, then there was a meter into millimeter. So another 10 to the 3. That makes 10 to the 6. Multiply by radius is 20. And the J for the solid is 2.5, 10 to the 5. That will give me an answer like that. Yeah, because we got everything in millimeter. If I give you an idea, that's 79.6 megapascal. Newton over millimeter square is megapascal. So you can write 79.6 megapascal. And in hollow one, it's 91.4. Yeah, so you can kind of get in shear. Now this is the hollow is more strong because when you try to twist the hollow one, it's more strong as compared to the solid one, because in the solid one the shear will start in the middle. So what I'm saying is, if you got a hollow, and maybe in bending it's a little bit different, yeah, but in shear it's always going to be a lot stronger.